All right, let's go ahead and talk about this one. In this little video, we're going to talk about the wavelength of light and the energy or the color of that light. So the core test, if I read exactly what it wants, it says to identify the relationship between wavelength and light energy. As you can see, I've drawn this. These represent wavelengths that are long. This represents wavelengths that are short. Now, wavelength is symbolized by this little thing right here called lambda. So that always means wavelength. And make sure and write down and know this sentence. It says wavelength, or lambda, is inversely. Inversely means as one goes up, one has to go down. It's inversely proportional to the energy. So as we can see right here, when the wavelengths are long, lots of space in between them, they have very low energy. Now, if we're talking about light, the long wavelengths would represent light that's a color red. Red actually is a color that is very low in energy. All right? As we go over, the wavelengths get closer. And if you just draw this picture, you'll even notice yourself. It was really easy and really slow to draw, but by the end you had to put in a lot of energy to draw those wavelengths really narrow. So short wavelength is very high in energy, and that would be blue or purple. I don't really have a purple marker. And this is the analogy I always used. Bear River is weak, and Box Elder is strong, or high in energy. And nothing against the bears, it just works for the color. Red, low energy, long wavelengths. Blue, high energy, short wavelength. Inversely proportional. The longer the wave, meaning the bigger the number, the lower the energy. The shorter the wave, meaning the smaller the number, wavelength, whatever, the higher the energy, and significantly higher. Okay, please, hopefully you have that. Right, now, this one, up next, we'll move it this way a little bit. I just want to review when light is actually produced in chemistry. And it has everything to do with the electron. And please always know that it has everything to do with when the electron returns from a higher orbital to a lower orbital. Okay? Light is only released when the electron falls. When the electron goes up, it required energy. And that wouldn't give out light. That would take energy in to promote the electron. So here we go. We have some source of energy coming in, like a microwave or something. It hits an electron that's hanging out in a lower energy level, represented by rings. We know that's not the model, but it's easier to draw. The electron jumps up, and then it falls back down. And when it falls back down, it releases light. If you have a small fall, you have low energy, you have long wavelength, and you have a red photon being released. Okay? The size of the fall, just like it would hurt more to you if you fell farther and shorter, the size of the fall of this electron determines its energy and thus its color when it's released. Okay, going over, now we have our energy coming in, striking this electron, making it jump to a farther out energy level, causing it then to fall back to where it previously was. Since it's a larger fall, we now have higher energy or shorter wavelength. Light, we would call that blue, and we'd say that came from a large fall. So a large fall creates a blue or purple-ish colored photon. And then finally, I can't hammer this enough, the energy of photon determines the color of light of the photon or the light released. Okay? Large falls, large energy, high energy wave. Color, purple, blue-ish. If we have small falls, we get into the reds, the orange, just like Roy G. Biv. Okay? Hopefully that will help you. Always remember that light's released when an electron falls to a lower energy